I am Dr. K.C. Jain, and we were discussing the electrodynamics. So we have discussed the curl and divergence of electric field, and now we will discuss about the magnetic field. So magnetic field, the electrostatic field is developed by static charge, and magnetostatics is developed by moving charge with constant velocity, and it is given by our state that a current carrying conductor is always surrounded by a magnetic field. Magnetic field is we can represent by the imaginary lines, and as we discussed that if we plot the magnetic field lines for a magnet, then the north pole and south pole, and the lines start from the north and ends at south, and this we can represent, and by the right-handed rules we can calculate the direction of the magnetic field. That thumb shows the magnetic field, and this thumb shows current, and curled fingers the direction of magnetic field. Now the same as in electric flux, we have magnetic flux, and we can write magnetic flux d phi b is equal to b dot ds, and it is equal to b ds cos theta, or phi b is, we can write surface integral b dot ds, and phi, the unit of phi is Weber. So magnetic flux density or magnetic induction B is total magnetic lines of force divided by area, that is Weber per meter square or Tesla, and we can write B is equal to mu 0 H, and H is magnetic flux, magnetic field density, and the value of mu 0 is 4 pi into 10 to the power minus 7 Henry per meter. Mu 0 is permeability, or simply we can write B is equal to mu H if there is a medium. Then the relative permeability mu R, we can write mu 0 upon mu naught. Now the Lorentz force. The Lorentz force is the determine the force experienced by a charged particle in the presence of electromagnetic field. So it involves the Lorentz force, both electric field and magnetic field. F is equal to Q E plus V cross B. So QE is basically the electric field, and Q into V cross B is the magnetic field, where V is velocity. So Biot-Savart's law and Amperes law are two major laws of magnetostatic field. So first we will discuss the Biot-Savart's law. Biot-Savart's law, if a current carrying conductor is there, that, and if I want to calculate the magnetic field at a distance r, then we can choose a point, and dB is directly proportional to the current, dl the line element, sine theta the angle between the vector and the current carrying conductor, and the distance r square. So dB is equal to k I dl sine theta upon r square. K, as we know, that mu 0 upon 4 pi. So dB we can write mu 0 upon 4 pi I dl into r square upon I dl into r unit vector divided by r square, or mu 0 upon 4 pi I dl into r vector divided by r cube. We can write this Biot-Savart's law in different form, that if the current carrying conductor is in the form of line, then we can write like this. If it is a surface current, then we can write like this, and if it is a volume current element, then we can write like this, where K is surface current density and J is volume current density. Here I is line current density, K surface current density, J volume current density, and we have used the line integral, surface integral, and volume integral for it. Now we will calculate the divergence and curl of magnetic field. So these are the two fundamental postulates of magnetostatics. So phi is, we can write d dot ds, that is equal to q. This is possible to have an isolated magnetic charge. So b dot ds is equal to 0 for closed surface. By divergence theorem, phi dot b dot ds is equal to del dot b, dv equal to 0, or del dot b is equal to 0. So divergence of a magnetostatics field is 0, And according to Amperes circuit law, the line integral of magnetic flux density B around any closed path is equal to B dot dl is equal to mu 0 I. By Stokes theorem, we can convert the line integral into surface integral. So B dot dl is, we can convert into surface integral, that is curl B del cross B ds, and it is equal to mu 0 I from the above equation. Or del cross B ds is equal to mu 0 j dot ds, that I we can write j dot ds. So del cross B is equal to mu 0 j. So curl of a magnetic field, or it is the differential form of Ampere's law, that we can write curl of magnetic field del cross B, it is equal to mu 0 j, and it is the differential form of Ampere's law. So differential form and integral form, we can write the quantities which we have studied. So del differential form, del dot E is equal to rho upon epsilon naught. In integral form, we can write integral E dot ds, that is equal to 1 upon epsilon naught rho dv. It is the Gauss's law. Now the net flux is 0, or non-existence of magnetic monopole. So del dot B is equal to 0, it is differential form, and B dot ds equal to 0, it is integral form. Conservation of electric field, that is del cross E is equal to 0, or E dot dl is equal to 0, that is integral form. Ampere's law in differential form, del cross B is mu 0 j. In integral form, B dot dl is equal to mu 0 j dot ds, that is Ampere's law. Now we will discuss the time varying field. In static electromagnetic field, E and B are independent, whereas in time varying electromagnetic field, E and B are interdependent. So in varying magnetic field act as a source of electric field, and vice versa, that if varying electric field will act as a source of magnetic field. So these results are based on Faraday's law of electromagnetic induction and concept of displacement current. So first we will discuss the Faraday's law, and then we will discuss the concept of displacement current. So Faraday's first law, that is changing magnetic field induces an EMF. Second law, induced EMF is equal to the rate of change of magnetic flux. So by second law, we can write induced EMF is minus d phi by dt. That is, induced EMF is equal to the rate of change of magnetic flux. So EMF is minus d phi by dt, or it is n d psi by dt. N is number of turns and psi is flux through each turn. The negative sign shows that it opposes the flux producing in the circuit, that is Lenz's law. So EMF is equal to E dot dl, as we know. So E dot dl is minus d phi by dt, and phi is equal to, we know that B dot ds. So we can convert like this. So we can change it, and by using Stokes theorem, we can write del cross E is equal to minus del B upon del T, and it is known as Faraday's law in differential form. Now we will discuss the equation of continuity, that charge always remains conservative, or we can say constant. So I is equal to, we can write minus dq upon dt, or I is equal to minus d upon dt. This q we can write rho dv, or I is equal to j dot ds. So j dot ds is d upon dt rho dv, and we can write like this, that rho is changing with respect to time. From Gauss's divergence theorem, we can convert it j dot ds in del dot j dv, and we can write it finally del dot j plus del rho upon del t is equal to 0, and del dot j is minus del rho upon del t, that is equation of continuity. For steady currents, del rho upon del t is equal to 0, or we can write del dot j equal to 0. Now the Maxwell's displacement current and correction in Ampere's law, that is important. So B dot dl is equal to mu 0 I, and in I we can write j dot ds. So from Stokes theorem, we can convert again B dot dl is del cross B ds. So it is mu 0 j dot ds, or del cross B is mu 0 j. On putting this in equation of continuity, we can write del cross B is mu 0 del rho upon del t. But we know that del cross B is equal to 0, or mu 0 del rho upon del t equal to 0. Rho is constant with respect to time here. Hence, Ampere's law is not valid for time varying fields. So according to Maxwell's, therefore it should be modified. Something must be added to J. So let it ZD, that is displacement current. So del cross B, we can write again, is equals to mu 0 J plus ZD. Taking divergence both sides, we can have del dot del cross B is 0 as we know. So mu 0 del dot J plus ZD is equal to 0, or del dot J plus ZD is 0, or del dot J is minus del dot ZD. But from equation of continuity, already we know del dot J is equal to minus del rho upon del T, and from the Gauss's law del dot D is equal to rho. So we can substitute these values. So del dot ZD is del rho upon del T equal to del upon del T, del dot D, and we can write like this. So finally we can write del cross B is equal to mu 0 J plus del D upon del T, or mu 0 J plus mu 0 epsilon naught del E upon del T. That is the correction in, or we can say it is the modified by Maxwell. JD here is displacement current.